Good morning, everyone.
Hi Farhan.
Hello. Uh, we will have to wait for some time. There are still very few participants.
Yeah, sure.
Okay. I think we will start and then people can join in. So, like I said yesterday, what we want to try today is adding more complexity to the world. We want to make it more realistic, and that is what we are going to do in today's session. So we will enable some sort of I won't call it intelligence, but at least some sort of dynamism in the behavior of the opponents. So they will also be able to move. We will I'll go through the instructions and show you exactly what we want to do today. We don't want to make a big leap in terms of the complexity, because then it will be difficult to find out why our algorithm is not able to perform. But we do want to make certain changes that makes the environment more realistic. Before that, I want to take a few moments and talk about the changes to the project rubric. So if you have been trying to solve the problem, the take home project, right? So the rubric uh, is here. Step 1, 2, 3 are the same as as they were earlier. I have changed the requirement for step 4 because it doesn't seem like uh, uh, that a reward of a cumulative reward of 9.0 is possible for 100 episodes. You will have episodes where you can even get a reward of 12 or more, but because the way the problem is set up, the reward basically depends on the length of the route that you take. That depends on where the passenger is, where the drop off point is. uh, and so the changes that I have made is that instead of asking for a consistent 9.0 reward for the 100 episodes, we are looking for the best and the worst performances, right? So if you look at step 4, it says that you have to take a window of size 100 episodes, and then you have to look at the bottom fifth percentile, which is the worst rewards that we are getting during these 100 episodes, and that should be 7.2 or higher. And if you look at the top fifth percentile, which is actually the 95th percentile of the overall rewards, so that should be 8.2 or higher, right? So your top your bottom 5% or so should be 7.2, and the top should be 8.2 or higher. Uh, the evaluation process is still the same, as you can go along evaluating your algorithm as you are training it, and just make sure that these criteria are met. So you're taking the average over 100 episodes, and then for the last 1,000 episodes, when you take these averages, so make sure that they are consistently between this range. So the percentile is 7.2 or higher, and the 95th percentile is 8.2 or higher. Is there any confusion?
So Farhan, are you saying that for the 1,000 episodes that we have for the last training part, we just divide into 100 sections each? So there's 1,000 and then 10 elements of that list, and then using that 10 average list, you use the 5/5 and the 95th, or?
So the way I was thinking about it was, let's say you are training for 50,000 episodes, right? And uh, you are tracking the reward for each episode, and then you take a moving average. So the moving average will be zero at or first episode to 100 episode, then second episode to 101st episode, and so on. So it's like sliding a window across your rewards,
I
and
see.
then finding the average. And then you just look at the last 1,000 such windows, and for those 1,000 windows, your reward should meet this criteria.
Wait, so the last 1,000 episode, are we just taking a mean of the 1,000 rewards?
uh, you don't need to take the mean, you need to find the fifth and 95th percentile, right? So for the last 1,000 you will have what, around 900 different values, right? When you apply the sliding window to the last 1,000 episodes, you will have 900 different values of the 100 episode average, right? So find the fifth percentile and find the 95th percentile, and then see where they lie.
I see. So within that last 1,000 episode, your sliding with window of 100 is constantly happening, and then using that list of averages, we take the fifth and the
Right.
95th. I see.
Right.
Okay.
And additionally, you just need to check that the algorithm is like, you can do this outside the training loop perhaps, or within the training loop as well. But during those last 1,000 episodes, there should be no wrong pickup or wrong drop off penalty, which is the penalty of minus 10 points that you get if you try to pick up or drop off at a wrong location.
So for that last part, do we need to show how we proved it? Like, do we need to provide some function or something that we have to
Yeah, a
list, or do
little
we just
bit
say
of
we
code,
are?
just keeping track with the variables. So if you set it to false, and if anywhere you can keep track of it throughout all the episodes, pretty much like we are doing with rewards. Or you can use some sort of alternative logic, but there should be somewhere in the code, it should be easy for me to see that this condition is also being met,
Okay.
right? If just plot it, just keep track, and keep track of whether or not your algorithm was penalized for each episode, and just plot the last 1,000 plot, or just test the last 1,000 episodes.
Okay. And for the hyperparameter adjustment, like, do we need to explain the logic behind like why something happened, or can we just list out that the average has been getting better with these parameters?
Yeah, I mean, I think I would like to see uh, how, like, what. So there is fundamentally no, methodical approach that we are following right now. It's more trial and error. But I would like to see a little bit of what that trial and error look like. So suppose if suppose you totally randomly tried four different things and one of them works out. So at least, in the comments, let me know that these are the other three combinations that you tried that didn't work out, and this one works out. And then if you suppose for a particular value of the learning rate is working out, so probably, try increasing and decreasing it a little bit, and see how it impacts the training process.
Okay. And I guess with the changed rubric, there shouldn't be any like new algorithm or anything that we didn't learn from the class we have to apply, right?
No,
Like it's
no,
just all.
it should be the standard stuff that we.
Okay.
Hey, Farhan, I have a question. So for like when we try to verify the average reward for the last 1000 episodes, so what I noticed is that if let's say if, my training algorithm use a minimum epsilon, then there's still like a 10% chance that even if my policy table is optimal, but it may randomly choose something, right? Can we like for the last um 1000 episodes training, we just turn off epsilon so that it always get the optimal policy that is following that
Okay,
table?
so so this rubric is more designed when you are evaluating within the training loop. If you want to follow that approach, uh, then I think the results will look pretty similar because that probability already. But it also depends on what minimum epsilon you have set. But if you think there is moderate chance that there are probabilistic actions that are sort of giving you bad rewards in between, then you can do this outside the training loop as well.
Okay, I see. Yeah, thanks.
Sure.
Hey, Farhan, I basically joined a little bit late. I basically didn't understand this, like the fifth percentile of 7.2 in the sense out of kind of like the 1,000 to whatever this, like the minimum possible rewards in like the bell curve, they need to be under
Yeah. So
7.2.
let's think of it in very simple terms. So thinking of the last 1,000 episodes, when you take a sliding window and when you take the sliding window average, then you will have one average for the first 100 episodes, and then another average for episode 2 to episode 101, and so on. And I'm talking about starting at the last last 1,000 episodes only, not from the beginning, not counting from the beginning. So you will have 900 or so different values, right? And then you can simply call the NumPy API for calculating its fifth percentile and its 95th percentile. The idea here is that get some measure of the best results you are getting and the worst results you are getting, and that should be a 7.2 for the fifth percentile and 8.2 for the 95th percentile.
Which API? I missed what you said.
NumPy has a quantile API, np.quantile, I think, that will directly give you the percentile.
So in this case, when you say like the 100 episode average means just among the 1,000 episode, we can break it into 0 to 99 and kind of 100 to 200, this kind of thing. So like totally there will be kind of 10 iterations. So 10.
Yeah. Uh, you can do that, but typically the way it is done is by just sliding a window. So it's like 0 to 99 and then 1 to 100 and then 2 to 101. That would mean you will have 900 different averages.
Oh, okay. Okay.
Because one episode can give you really disastrous results.
Okay.
So
Okay.
it makes a lot more sense to like slide it in that way.
Okay. Sure. Now I understand.
Okay. And if there are any concerns about this, please let me know in Slack. But now I'm going back to today's notebook. So we are in week 4, session 2 on the master branch. I just pasted the link in the chat box, and I have it open in Google Colab right now. So please open the notebook. Then I'm going to talk about the changes that we want to make, why we want to make those changes. And the code is largely already present because it's really, really difficult to do that in a 2-hour session where I give you a description and then I assume that you implement it live here. But we do want to do a very thorough walkthrough of the code so we understand what changes we have implemented and why we have made those changes. And we are slowly sort of moving towards a more deep learning approach. I'll talk about that a little later when we come uh, to the step where we have to think about encoding the state. but get the notebooks first. So okay, so yep, I'm jumping to Google Colab where I already have the notebook open. This is Foosball version 3, and you can see the changes that we have made since version 1 highlighted here, right? Some of these changes we already implemented in version 2, but I'm anyway going to talk about them again. So the first change that we made was about introducing uncertainty in terms of actions, right? This is what we discussed at length in yesterday's session, and there was some confusion as well. But really, what we want to implement is that anytime you take an action A, there is a small chance that instead of the desired action being executed, one of the other possible actions are carried out. So B, C, D, whatever actions are possible, excluding A, they are carried out, and that will make that will result in a different next state and a different reward, and that is something that the agent will have to learn over time. And we sort of saw this that by tweaking our parameters a little bit, when we implemented this logic, we did two changes. We did so the change we made to the environment yesterday was basically we created a three-dimensional table that mapped every state, every action to all the possible next states, right? And that was pre-filled, and we spent a great deal of time understanding how that is being done and how the probabilities are being calculated. But that is how we implemented uncertainty, and after that we went through the same uh, approaches like sarsa and q-learning, and we saw that if we tweak the parameters a little bit, we sort of get good performance. So the agent is able to learn that there is some underlying uncertainty, and it learns to take the best actions possible even in the face of that uncertainty, right? uh, so this is this the idea is clear. We are going to approach it a little differently today, because we'll see that constructing that huge table which was state into number of actions into number of states, so that can become unwieldy if your number of states is really high. So we're not going to create the table for today's implementation, but this behavior is still there. The other change is that the opponents that were static earlier, they are dynamic now. We will see how they can move around the field, but they are not fixed in their place anymore. And yep, and they basically move independent of each other. Uh, the other two things that are still fixed is the initial position. So the game still starts with the ball in the top left corner, and the goal post is still at the bottom right. Uh, okay, talking about the details, the first change. So we want the players to move. We want the opponents to move around, the defenders to move around, and that means that you cannot predict in the beginning what the state will be when after one step or a few steps, right? So by state I mean where the defenders will be. So you cannot chart out a course through the field, avoiding the defenders, because the defenders are changing positions dynamically. Right. So we had to introduce a new action. We are calling it X, and X basically means that the agent decides to wait. So it will hold the ball in position, and it won't go to any of the adjacent cells. So we are allowing for that. Um, the second step is what I just described, and then there's another minor change which I just did for the sake of experimentation, which is that earlier whenever you hit a defender, the game was over. There was a penalty of -5, and the game was over immediately. That is not the case anymore. We want the game to continue. We will still have the same penalty of -5 points. Right. Rest of the rules are same, but talking about how the agents can move around. So right now we don't want to give them total flexibility. We don't want to just let them move around the field anywhere. Right now we are restricting them to their own column, right? So if you think of this agent, for example. So it can go down all the way to the bottom, it can go up. At any step, any of the agents will do take this action, one of these actions randomly. So if this agent, for example, this agent is here in the beginning, at in the next step it can decide to go up, it can decide to go down, or it can decide to remain in the cell. So there are three actions possible for the opponents, and the three are equiprobable, right? uh,
Just one question. So in this case, can this like opponents in the same column, can they have a collision? I mean,
yeah, no,
because it
we
seems that if one is coming up and is coming down in column 3, there is a
right,
collision.
right. We will avoid that in the code logic. We will avoid that. So when this opponent is trying to go down, for example, and if this opponent is already in that cell, so we will avoid that situation. The second opponent will not make that move.
Okay.
All right, so these are the changes. The other big change is, which sort of is made necessary by these other changes, is now the agent or the algorithm needs access to more information, right? It cannot be blind uh, to how the agents are moving, and that means that when it is planning, when it is deciding how to move, it will require some information about the agents. Of course, we can just pass it the entire array and let it see where the other opponents are. But again, that is not very realistic, because any agent, any algorithm will have only a finite horizon over which it can see. Whether it's a computer game or it's a real world scenario, you can only see so far in the future in terms of time and space both, right? So what is generally implemented is uh, that you are able to see a subset of the actual state. So now if you think about the game state, now it is going to be where the position of the ball basically, which you can say the state of the ball, and as well as the position of the each of the opponents, right? And because the opponents are only free to move vertically, so you can say that each of them can take on four different positions at max. So there are five of them, so it's like 5 to the power 4 different possibilities for these defenders, and 20 different positions for the ball, right? uh, but talking about observation versus state, so this is the state, which is going to be 20 multiplied by 5 to the power 4 or so. But what the agent should not be able to see the entire field. That sort of defeats the purpose of making the environment more realistic. So we will restrict the sort of what you can call the field of view of the agent, and we will only allow it to sense neighboring cells. So if the agent is here, it can only see this cell to its east, and this cell to its south. And of course, because north and west are unavailable, so it it can try to sense, but it won't find any defenders there. So we want to modify our code to account for this as well. So the game will internally track everything, the movement of all the defenders, but we only pass a subset of that information. So we only pass, for example, an array of size 4, which has which has a bit for each of the four positions, and we set it to 1 or 0 to let the agent or algorithm know which positions have a defender and which positions are empty, right? So I'll execute this cell. Okay, now there are a few questions that we need to think about. For example, um, the first question is, what information should make up the state of the environment per agent and the agent now? So I sort of already answered that. The information you want to track is the position of the ball and the position of the agents. But if you think, uh, you know, think about it more deeply, then there are different ways of representing the same information, right? uh, so one way which in terms of representation is very easy, is that we can take a vector, uh, or a list of size 20, and we can mark the positions uh, of the ball and the defenders with different digits on it, right? So what we can do is take a vector of size 20, if which is like, this field, and which has been converted into one dimensional array, and then wherever you find an agent, put a one. Sorry, wherever you find a defender, you can put a one. Wherever you find an empty cell or empty position, undefended position, you put a zero perhaps. And wherever you find a ball, that you can put a two there perhaps, right? And that will encode every state distinctively, so there will be no confusion between two different states. But then the number of possibilities is becomes really big, right? Because if you think of each cell, it can, one of the cells will have just each cell can typically assume one of the three values, right? 0, 1, or 2. So very roughly there are 3 to 20, 3 to power 20 different possible states. Most of those states will not be actually occupied, or they will never occur because there are restrictions. So the actual number of states will be smaller. But if you choose this encoding, then you have to somehow represent 3 to the power 20 different possibilities, which is a big number, right? We can adopt different approaches. So we will see how exactly we are doing that. But depending on how you choose to encode the state, the number of states will vary. Uh, the second question is how and why should the state be encoded? We will come to this a little bit later when we try to see how to build an algorithm to that can learn from this environment. And this environment is a little different from the previous one in terms of how it represents the state. Okay, the other question is yeah, state calculation and reward calculation, right? So earlier we had two different private APIs. One was called next state on action, which gave you the state, and then there was separate API for calculating this the reward from the state transition, right? Now that doesn't seem possible now. That seems difficult or maybe impossible to do now, because for example, think of the situation where you take an action that resulted in an outside, right? So the state transition is going to the from to going to be from this state again to the same state, right? uh, and then there is another possibility that the agent tried to just hold the ball in the current state, right? Take the action x. So for example, if you think about the top left corner, if you take the action north, if you take the action west, or if you take the action X, which is holding, in all three cases, the reward is going to be same, right? Sorry, the next state is going to be same. You will still be in state zero. So, but we may not have a reward defined for both of these cases, because going north or going west, that amounts to performing an outside. So for that we already have a reward defined. But the reward for just holding the ball in place, that could be zero, that could be undefined, that could be a different number. So you really cannot just look at the state and the next state and say what the reward should be. You should include the full information, which is what was the action taken and what was the state transition, and then decide if you want to reward or penalize the agent or not. Okay. There is another bit that we need to think about, which is, so this is a simulation. So how this is not a physical world. So uh, only one thing can happen in one step. Or when you call the step API, so things can occur in different orders. So for example, when I'm trying to simulate this game now, I have to move the player, then I have to move each of the opponents, right? And that can be done in different orders. Uh, I can move the player first, or I can move the opponent first, right? And in cases where their states overlap, I will have to think about whether where the order of execution has any effect on the outcomes or not, right? So if the player moves first, in this case, there isn't any difference. So where the, even if the opponent was there, then the player ends up there, then it's a collision. If the player was there and the opponent came to the player's cell, even then it's considered a collision. But there could be cases where you want to differentiate between the two, right? Um, yes, so these are the changes that we want to make, and I hope it's clear why we want to do that. Now I'm going to talk about the changes in terms of the code. So we have actually reduced the size of the code because there are a few functions which have been sort of brought into inside the step function. But I'll go top to bottom. So this function, this method was already here. It has only been renamed because it was a little confusing, because it was two indices and from two state. It was called two state and two indices earlier, but state is a little confusing right now because there are different sort of states. We can talk about the state of the player, the state of the opponents, and we can talk about the overall state, which is what we are interested in. So I've just renamed them to encode indices and decode indices, but there's no other change. Then there's a function, this one make observation, that we will come back to a little later. But first I want to talk about deserialize. It still takes all the same parameters. The logic over here is same. Uh, but then we had self dot player, self dot goal state, and self dot opponent states. We had three different sort of states. Now we are not storing them separately, right? So these are just temporary variables that I'm creating inside this method. They are not going to be stored in the object, right? I'll explain why this is so. But the rest of the logic is again very similar, except for one change over here, because earlier we were erasing the position of the ball or the agent from the field, right? But now we are doing the same thing for opponents as well, because again they are going to move, so it makes sense to store their positions separately, and then whenever we want to render, we just superimpose their positions on top of the field. So other than this line, there isn't any big change, right? The big change is sort of here. So now, earlier initial state was just the state of the player. Now it's a dictionary. So there is the state of the player, there is the state of the opponents, which is actually a list of states, and then there's a goal state, which is the position of the goal. Right? This is the sort of big change. And coming down to init, it is still calling self dot deserialize to initialize the current state. But now we have to remember that this state is not going to be a single integer. It's going to look like a dictionary with agent and opponent and goal states inside it, right? And then we have made changes here. We included a new action, and we were already passing a probability, slip probability. So we are just storing that slip probability over here. So earlier, if you look at version 2, and I want to quickly show you the diff. Yeah.
What is the like the new action? So you have added new action called like the X is going to kind of go out and come back to original position, or
So X means you are not making a move. You are just staying in the cell.
okay.
Farhan, for the goal state, goal
Yeah.
doesn't move, so can't we just put it as is?
Yeah, so it's rather provisional, because if a later stage we want to build something where we want to include, like, have goals in different position, which doesn't make a lot of sense. But if you want to experiment with that, that should also be possible. But technically, strictly, it's not needed. We can just omit goal state from this dictionary. We can just this dictionary over here. So we can just have agent and players.
Yeah, I see. Okay.
So I was trying to show you the diff. Right. This is our diff function, the older diff function which we had in version 2, and this is in version 3. And if you look at it, other than this change over here where we have added X, There is another change. So right now we are just storing this slip probability into a variable in the object, and earlier we were calling this function set state transitions, right? We don't want to build this transition table for today's implementation because this is going to be huge. We talked about the possible number of states. We will see that the number of states can be compacted if you encode it properly, more efficiently. But even then, it is going to be a big state table. So we will do whenever we take an action, we will still account for the possibility that there is some uncertainty, but we are not going to do that computation upfront and store everything in the p table. Okay, so this is how init is set up. Set rewards remains exactly the same. uh, Reset is interesting. So reset is again in terms of the code, it looks and feels the same, but now the state is going to be a dictionary. The steps are all the same: state, initializing the state and clearing the done flag. The other sort of difference is, I'm going to come back to this a little bit later, but now earlier it used to return self dot state, right? Reset would just return the state. So if you do that right now, you would be returning the entire dictionary, which will have the position of the position or state of the ball, and the state of all the players and the goalpost. But we don't want to do that, and I'll come to that in a few minutes. Let's talk about the step function first. So step API still looks the same. It takes an action. It wants to simulate that action. What has changed is that first of all, the first thing we are doing here is emulating the uncertainty, the stochastic nature of the environment. So we take the action, and then we compute the probabilities for that action being taken versus one of the other actions being taken, right? So we talked a little bit about these probabilities, but basically the slip probability that we are passing, that is distributed over all the other bad actions, and then one minus slip probability that is distributed over uh, the action, that the desired action, right? And then we pick an action which we are calling executed action, which is actually being executed inside the environment, and that we get that by sampling these actions with these probabilities, right? So the idea is same, but earlier we were doing this. We just created a table in the beginning, and then we would just look up things. Now we are doing it on the fly for every step, and these probabilities are of course going to be constant for every step. So there is no change from one episode to the next one, or one step to the next one. Okay, after that, over here, this is what we were doing in the function where in the function that we used to call get next state on action. So we have sort of absorbed this into the step function. Again, this can be refactored into smaller functions, but in the beginning it's good to have all the logic over here so we understand how this is working. So the simulation remains more or less the same. You take the player's position, you decode it into row and column, and then you see if the player is able to make the move according to the action that we selected here. So executed action, we take this executed action from here, and then we look up the delta, the row and column delta, and we compute the new rows and columns. And then yeah, so then we are basically checking for the same condition that we used to do earlier, which is if this is inside the bounds, then we are setting new player position to as per the new row and new column values, and we are setting this flag outside is equal to false. But if the new player otherwise if these are invalid, then we are setting the new player position to the old player position, and we are setting outside to true, right? Um, and the third bit is over here, which is simulating each of the opponents, right? And this is a little involved, so perhaps it will require some reading through the code to understand exactly how this is being done. but the rough idea is the same that we discussed earlier. So there are three possible actions: north, south, or staying put, and we are sort of simulating those actions for the opponents. For each of the opponents, you execute the action. So you start with one of the opponents, maybe the leftmost one, the first one in your list, and then you try to move it, and depending on the action, it may move or may not move. And when you're trying to move it, you check that it is not colliding with any of the other players at that point, whatever their positions are, right? So this is not exactly a parallel update to all the positions. This is more like sequential. So you move the first player, and when you're moving the first player, you are checking the earlier position of all the players. Then you move the second player, so the first player's position has moved, but the rest of the players are still in their position. And now you are checking against the new position of the first player and the old position of the other players which are yet to be updated, right?
So Farhan, the opponent is allowed to come in contact with the agent.
Sorry, the
The opponent is allowed to move to the agent's position.
right. The opponent can move to the agent's position, and of course, like it was earlier, the agent can also move to opponent's position. So you can look at the check here, right? So all we are checking for is whether or not it is another opponent and the defender or not. So we don't want two defenders to collide, and we don't want our defender to go into the goal post. But we are not really checking if it's colliding with the player. That will be done later. So it's totally possible that defender moves to our player. Even if the player decides to stay put in a cell, the defender can come to the player if if it is within reach of the defender. And we will see this in action in a little bit. But then this is the whole reward calculation. Now there are a few possibilities, and they have some overlap within them. So what we do is we define a reward variable which is 0, and the done flag is false. And then there's a variable which is basically tracking if it was a normal move, or if it was a move that resulted in a goal being scored or a collision happening, right? So the first test we do is if this is goal position. If you just converted a goal, then the reward is updated. We set done to true, and we set normal move to false, because this is not considering a normal move. This is a move where you are getting a different reward, right? Normal is basically keeping track of rewards where you either stay put or you take an action and come back to the same state. And then the second one is basically tracking collisions with the opponent, and we are rewarding them, rewarding the algorithm accordingly. And still normal is being set to false. You would notice that done is only being set to true here. So we have changed the behavior a little bit. So in this case, when you collide with an opponent, there will be an instantaneous penalty, but then the game still goes on. You can get out of that cell, you can still proceed with the game. Then we
So Farhan, if you go up, are you allowing the opponent to go out of the map?
no. Where would that happen?
Like in the above, if you go up.
Further up?
Yeah, this one. So in that for loop, like there for the player, you make sure that if it's outside of that if statement, in the else you put the new player to the original player position.
Right.
But then for the for loop for the opponent's movement,
Right.
like we're just if they're in like the top corner and they have the north for np.random choice, aren't we just allowing it to go up? Because you're changing the new row, new column, right?
But isn't that this condition taking care of that? This is where we are checking if the opponent is still the new row for the opponent and the new column for the opponent is still within the bounds.
So shouldn't the new position else be the current position?
No, so this is the case when you are within the bounds. So new position should be updated, right?
So in
Oh,
the
you are
case
saying
that it doesn't fall into this, right? Like if
yes.
you go out of
Yes.
outside of that, you're not doing anything, right?
Yes. So you're saying there should be an else over here, right?
Yeah.
Yes, I think you're right. Um, we're creating copy. Yes. Yes, I think there has to be an else over here.
Probably you don't, right? Because you initialize the new opponent position to the original one. And if it's not within
Yeah.
the bounds, then
Yeah. So we are creating this copy over here, right?
yeah,
Yeah.
Oh, I
So
see.
so
Okay. Yeah.
so yeah.
you need
Yeah.
the else.
Yes. It's not strictly needed. So it will stay put in its position.
I see. Okay.
Cool. Right. So this was the reward, and the done flag being updated, and then we really update the state the state variable, which is the current state. So we just pick the new player position, new opponent position, and the goal position remains the same. Uh, but then comes this change where we are computing something called an observation. We are calling a function called make observation, and this is the idea that we talked about earlier, which is we don't want to expose the whole state. We could have returned this state dictionary to the algorithm, but we don't want that. We want to simulate a more realistic version where the algorithm can only see to a certain degree, to a certain distance, to a certain radius around it or ahead of it, and that depends on exactly what sort of environment you want to build and what sort of visibility you want to provide. But in a very simple implementation, what we are doing is we are just letting it peek into the four adjacent cells, right? And that is where make observation comes into picture. And I'll go back to this code. So make observation, uh, it basically, the idea is that uh, we will return two pieces of information. One is the player's position, which we are just which we are just calling the player observation, right? So this is the part of the current state, which represents the position of the player. So this is one bit that we will send back to the algorithm from the reset function and from the step function, both of them. So we take the player position, and the other thing we want to do is we want to find out how many uh, opponents or defenders are present in the four adjoining cells. So the logic is again same. From the player position, we get its row and column, and then we have a delta defined for the four possible relative positions. And then there is another dictionary that we are calling opponent observation. And really, what we are going to return is player observation, which we already have, and opponent observation that we want to build up inside this for loop, right? And it's very simple. You just we will just compute the row and column, right? And then we will check if the row and column. So we have the players row and column. We will add the delta that gives us the four rows and columns corresponding to the cell to the left, top, bottom, and right. We just need to check if these are valid cells, and if they are valid, and there is a defender present there, we need to set one of whatever that position is. We need to send the corresponding none to one. uh, Otherwise we need to set it to 0, right? This is all we have to do here. But the idea is really simple, that we are just taking 4 bits of information, not including the entire state, and then we will return this tuple, which is the player observation and opponent opposition. So we are still not passing the goal state. We can do that, but right now we aren't. So look at this code, and I hope you understand the rest of the logic. So try to implement this, uh, you know the remaining of make observations, and then we can jump to the next state where we are creating a new object, and this will have different properties. So we'll again explore the environment a little bit, and then think about how to use the existing algorithms. So take a few minutes please and try to implement the to do part here. Okay, so this should be a small change. The logic is pretty much like what we have written earlier when we were trying to move the agent, right? Only this time we are scanning the neighboring cells. We're not really moving the agent anywhere. The first thing we need to do is find the row and column where we need to look for. So k is changing, so delta k will change, and we use the deltas to find the row and the column where we need to look for an opponent. And then there is the usual condition, which is that this is within the bounds of the field. Right, so there is this if condition. The first two parts are basically checking that the row and column, they are within the bounds, but there is a third condition which is checking that this position actually has an opponent, right? So what we do is we take the scan row and scan column. This is the position that we are testing, and we convert it into a state. We're calling this API, and then we compare, and then we just see if that state is present in the opponent states, right? So it could be done in different ways. You could have scanned over the opponents and then compare their row and column with it, but because the state is unique, we can just compare the state and see if there's a collision or not, right? And then of course there's an else part. So if any of these conditions is false, if you're outside the bounds, or if your opponent is not present, so in both cases we need to set it to 0. So this dictionary will have a 0 or 1 for each of the 4 possible relative locations. That completes the code. If everything is fine, we should be able to run the next cell. In my case, it runs without any error. And then if you run the next one, so it still looks and feels like what we had earlier. But now we can run the next cell and see how the probabilistic actions are affecting, how the dynamism is functioning. So right, so I reset the game, and the first thing we notice is that now we are getting this big dictionary. It's a tuple of a number and a dictionary, and we know that the first thing, the first element is the state of the ball, and then the dictionary is representing the information, what we can call the observation from the perspective of an agent or an algorithm. So this is what we are able to observe. You can see that there is so two of the adjoining cells are definitely not present at all, but the other two are, but they don't have uh, any opponents there. So we have north, east, west, and south. They're all zeros, right? Now I'll try taking a step perhaps to the east, right? And that takes me to state 1, which we can see here. And we can also see that and now there is 2 1s here corresponding to east and south, which you can also see in the field being printed here, right? So there is an opponent to the east and the south, and the rest of the information is what we had earlier. So there is the immediate reward, which is -1, and then you have the done flag, which is false right now. Now I will want to come back, because and you should also notice that between this step and this step, this opponent has actually moved up by 1 position, right? So it was here in the middle, now it has climbed to this second row, and so this is like a checkmate for us, and we need to move out and go back. This is something that the policy will have to learn, the algorithm will have to learn. So let's try to go back west, right? And then I can make a few moves down south. South is safe because the opponents cannot really move left or right. So these opponents cannot come over here and block my path. So I can try going south for a few time steps uh, to stay clear of the opponents. Right, and you can see that in some of these steps, the opponents are changing their positions. We could have made these opponents more intelligent, we could have added some sort of tracking where the opponents are also able to track where the agent is and then try to block it, try to either block the agent or block the goalpost. But we aren't doing any of that because we don't want to add a lot of complexity in one go. So go south once more, and then east, east, and east. Right. So fortunately, I'm able to score a goal. Now I must reset the game because I also want to show you what happens in when there's a collision. Let's try to go east twice. Oops, the player has changed. I'll try going south. Yep, this time there's a collision. This player didn't move, but I did move down. So there is a collision here, but the game is still going on. I can recover from this collision. I can go east, for example, right? So I decided to go east, and the opponent decided to go up. So we have both parted ways. The opponent is here, I'm here, and then I can continue. Right. I can also take the new action, which is X. So things have changed a little. Earlier, we would use X to stop this loop, but now X is one of the actions. So if I take X, then right. What happened here? X is supposed to hold the ball in position, but why did I end up here? This is because we also have these actions which have probability built into them. So probably because I took one of the bad actions, like the environment took a bad action. I instructed the environment to go to stay put, but perhaps it took a west action. Let me check that by executing X again. Right, this time I'm still in the same position. Right, uh, maybe once more. Yep, I'm still in the same position. So with X, I can, stop myself in this position. So this is also necessary because there will be situations where you are perhaps surrounded from different sides, and you just want to wait and watch until the defender is clear, and then you want to move. This gives us that possibility. But I'll just stop the game with Q, and you can already see that everything we implemented in terms of the logic that seems to be working. Right, so all the changes, we have a different you know type of state that is being returned. We also have different rules. The rules seem to be working. So it's again time to go back and see if we can solve this new environment using the same old approach, or if we need to tweak anything. Okay, so if this is running, then we will just
Fran, I have one more question about the reward. If you go up to the where we assign the reward for the goal, opponent, and the outside.
yep. So the reward is same that we were using last time.
Yeah. So I tried like moving the player to where the opponent is, and the opponent sometimes can move upward south as well, right? So there's actually no collision. So in that case, if you go down to the step function.
Right. The reward calculation part, right?
Yeah. So shouldn't it be the new player position in new opponent position in that case to get the reward of opponent, which is -5?
This one, right?
Yeah, because you're just going to the opponent position, which got updated to the new opponent position right above, right?
Yes, you are right. Yes, you are right. There should be new opponent positions. That is a bug. There should be new opponent positions.
I don't think so. I think it should be the old opponent position
Uh,
because if your player is above the opponent moves up and you moves down, then you actually miss that collision, right? So
so
Yes.
we are simulating the player first, right? So you the new player position is where the player has ended up now, and then new opponent position is where the opponent hasn't the position where the opponent is now. So it makes sense to test it in this way.
well, but if originally your player is above that opponent, now you move opponent down, you move player down, you move opponent up,
Yeah, yeah,
then you miss
yeah.
missed that
Right,
collision.
right. So I'm getting what you're saying. So yes. So before
But that should be -1 for the reward, right? Like it shouldn't be -5 because there's no collision happening. Like the
so
chance
in
that the opponent goes up and the player goes down and there's no collision happening, isn't that just step of -1?
yeah, so I think the question was that you move the player, right, and the player ends up into the old position. So I think that shouldn't be considered, that shouldn't be a possibility because we want to simulate both. We move the player, then we try to move the opponent, and then we test with respect to the new position of the opponent. It's like you can consider it as one atomic operation. So when both have moved, then we test if they are still in the same cell. Does that answer the question?
Yeah, putting in the new opening position makes sense to me for this function.
Yep. It should make sense because we are simulating this, so you have to think about what a more realistic scenario will be. Um, so in the real world, this part happens parallelly, right? So both the physical entities, they are free to move. So if the player is coming to collide with the opponent could be moving out simultaneously. So we really need to, if we sort of discretize that, we really need to think about
But you
where the
don't.
player ends
The
up.
thing is, you're not giving the thing enough information then, because the problem is take the situation, like the situation that was being described, where the guy, where, like, actually take it a situation where you're somewhere, the opponent is to your northeast. Okay, the agent has no information that currently there's no information that the thing is the northeast. So the agent has no idea the northeast is a bad,
Right,
the east is
right.
even a risky situation, right?
Yes.
That's something that it could, what's going to end up happening is that maybe that gets baked in just because of our map, right? Based on our map, it's going to get baked in that it's going to know certain locations are risky to move through. But
Yes. Yes, so we should probably make our observation more realistic by having a fixed sort of radius or field of view that you can look into. So that should include every cell which is directly connected or which is even diagonally present, anywhere from where an opponent can, come and intercept you in the next step, right?
either way, this
That
seems
that
like both situations are, you probably don't want to, like, should it not be penalized for moving over top of a player? Like if you put it as a new opponent position and it gets lucky and the guy moves out of the way, that wasn't necessarily a good move, right? Like that was,
yes, this happened
because
by
the
chance only,
ideal
and
thing to
we got
do is, if you're
right.
observing that the opponent is in the spot you want to be in, the right move is to stay still, right? Like,
Yes. That is something that we want to think about. So probably we want to check against both the new position and the right position, and perhaps also have different rewards, right? One when you actually collide versus when you took a risky action.
But it's really a matter of the player's observation state, right? Like, because if the opponent is like 2 cells to the right, and we want to go to the right towards the closer to the goalpost, and we actually don't know that the opponent is there 2 cells,
Yeah.
and then if it's able to move to the left, then we collide anyways. So even if it's diagonal and we only know the left, right, or up, north, south, isn't that okay in terms of the observation state? Like it's just a scope of the player.
Yeah, so the question is, should we update the observability? Should we try to make it more realistic, more representative of the real world, where we will happen to look a little farther out and think about those type cases as well, or not? And also about the reward structure. So if it was within my field of view at that time, then I shouldn't probably have taken a step in that direction. So in this case, the collision didn't happen because the opponent decided to move out of the way, not because the agent took an intelligent decision. So the question is, should we include another reward for or penalty for the case where in the previous step the opponent was in front of you, and then no matter whatever happened in the next step. So if there was an actual collision, there is already a penalty. But even if there was no collision, but you saw that coming, so shouldn't you have avoided that? That is a separate question.
Yeah.
Cool. This is very important, and we should come back and see if changing those things, including a different reward, will help or not. But just go down a little bit. Yes, this is all going to be pretty similar. There are no changes. Get discounted return doesn't really get impacted by how you implement the environment. So I'll just run this cell. Right. This implementation over here, it has slightly changed. So earlier, because we had access to all sort of inside information about the game, so we knew how many states were there. We also knew how many terminal states there were. So we were explicitly, when we were crafting the policy, we were explicitly skipping over these states, right? So we didn't want to define a policy for any of the terminal states. That won't be possible anymore. We have removed that API. We don't know in advance which terminal states are there. So we will just define a policy for a terminal state, but we will never really execute it because the done flag is there. So whenever the environment tells us that it is done, the episode is over, then we should factor that information in, and we shouldn't really try to take any actions because there will be some sort of an action defined even for terminal states. So that is the change over here. In pretty print, this part, the none part, is not really required because now we will have a policy for every cell, including terminal states. You can remove this. And the rest of the code is again going to be pretty similar. Uh, the difference, of course, is that it is a lot harder to understand, like look at an episode and make out what exactly is going on because there's so much information to deal with. But we sort of know what these things represent. So if you look closer, you'll be able to understand. Right now, these episode strings are going to be really long, and they have a lot of information. Discounted returns, there is no real change over here. Right. Yeah. So the only change is that, again, the first list that it returns, that is going to look very complex because it has all these dictionaries within it representing each of the states. So that is the only difference. Right. Uh, this function is again going to be the same. It doesn't require any changes. Now basically we want to go back and use the same algorithm. So we had, I think, 4 different or 3 different variants. One was the constant alpha where we were using the full episodes, and then there were 2 different TD algorithms, temporal difference algorithms. One was SARSA, one was Q-learning. So we want to run those algorithms, but now there is another problem that we need to deal with, right? So what we want to do is again fill up the estimated returns table, but the returns table has a row corresponding to every state, and it has a column for every action. The problem is that now the state is so complex that you can't really use it as an integer to index into that table and to find the appropriate row where you want to store things, right? And that is what we want to do in this intermediate step over here. So we want 2 functions, one that can go from the observation you are getting. So it can take an observation and then output an integer, and then also it can take which we will call our state, which will be the state from the algorithm's perspective. And then it can also take, the other function should be able to take this state and then decode the observations back. Right. So now we will go into breakout rooms and see how we can encode this efficiently.
Hey, Farhan, you were saying earlier that the number of states was 3 to the power of 20. How did you get that?
That was depend. So number of states will depend on how you choose to represent it. The representation we were talking about, where you take a list, and then every entry in the list will be either 0 or 1 or 2. So 0 will stand for empty if that cell is empty. 1 will stand if that cell has perhaps an opponent, and 2 if it has the player.
I see. Okay.
But we definitely don't want to use that encoding, and we don't have the entire state. We don't want to track all the players. We have just 4 adjacent cells.
Hey, Kaushik. I mean, you, you, yeah. Well, that it's unavoidable. It keeps popping up in the everywhere. Yeah, but I mean, you look at the Qualcomm stock since I joined. It was like
Hey, Fahan. Can you hear me? Okay. So, just want to get some further clarification on the collision detection. So I think comparing the new player state with the new opponent state makes sense in most of the cases. But I think there will be one case which should be a collision but might be missing, which is if the player is to the north of the opponent, and now for the next move, player decides to move down, and opponent decides to move up. So they just cross each other, right? In this case, the code won't detect it as a collision, but I think in reality that should be a collision.
Yeah, that is open to interpretation for us. Uh, yes, there is, in real world you cannot just transport the other two or swap their positions without a collision. So if you want to implement that, we can add a condition for that. If we think it's just a game, it's possible for the player and opponent to cross paths without actually colliding. If you strictly define collision as when they end up being in the same cell, then it's not a collision.
Yeah. Okay.
Sure. Okay, seems like everyone is back. So, did anyone try to implement this? This is what I attempted. I am still not 100% sure this is error free. But basically, when you are trying to encode an observation, so the observation itself is made up of, it is going to look a bit like this, right? So I'll actually have to remove one of the indices from there. But the idea is I was just passing all the information, right? So uh, in its current form, for example, I'm passing it episode of 0. So episode of 0 is much more than, yep. It's much more than the observation. It has the observation part, which is this tuple, and then it has the action, and then it has the reward as well. So I have to fix my definition, but the general idea was that if you just look at this part, so what is the observation part composed of? It has a state for the player, which can be between 0 and 20, and it has 4 bits of information for the opponents, right? Whether they are present or not, right? So if you think about it, for every possible state that the player in, generally there are 16 different possibilities with respect to the opponents, right? Because each of the neighboring state, it could be occupied by an opponent or not, right? So in the most general sense, there are 16 possibilities for each of the states, which means if the player can be in 20 different states, then uh, there are 320 different overall states possible, because for each of the player's state there are 16 possible states for the opponent's configuration, and that gives you overall 320 states. Now the question is, how do you encode this so that every possibility is distinct? They don't there's no conflict between different encodings of different states, right? So like I said, for every state of the player there are 16 possibilities uh, for the opponents, right? And so what we can do, so you can think of that when the state is 0, then the opponent configuration can be mapped to numbers 0 and 15, which are 16 different numbers. When the state is 1, then the opponent positions can be mapped from 16 to 31, which is the next 16 numbers, and so on, right? And so what you're basically doing is you are multiplying uh, the state, which is the player's state, you are multiplying that by 16, and then you are just adding the configuration which the opponents are. You're converting that into sort of a bit vector representing a number between 0 and 15, and you are adding that, right? Is this making sense to everyone? And I have to get rid of right. I think this will work. This is episode 0. If I just want to encode its observation part, I will just take episode 00. Let's remove this for the time being. Okay, that is interesting. String basis must be integers. Did anyone else try to implement this?
I did it, but I did it the other way. Like I put the
Okay, the states to the left.
Yeah.
Yeah, that should also work.
Yeah, I just had a binary to decimal converter between the Northeast Southwest dictionary and the number.
Yes, that is what I'm trying to do, but I'm getting this weird error. Ops 0.
Should I share what I had?
Yeah, but just give me a minute. Let me try to debug this first.
Why do you have a plus plus on line 5?
Okay, this could be causing issues. It has something to do with indexing. Right, so where is the south coming from? Observation.
Should I share mine?
Yeah, please.
There's like 2 lines. Oh, you have to stop, I think.
You can share now.
Do you see it?
Yep.
Yeah, so it's basically just these 2 lines, right? So I have the
Right.
encoder. It's the same thing that you're trying to do, right? I
Yes.
take the first input times 16 plus binary to decimal, the second input, and the binary to decimal is just
That's right.
that.
Right. Yep. It's the same thing. Something. There's some very subtle, simple error there. But if you can just copy paste this
Yeah.
into Slack, we'll copy it over.
Oh, into Slack.
If you have Slack running, otherwise, I will have to type it.
Come into the, here it is. In here?
Yep. Thank you. Right. So we need something like this. Right. We need to call this function, and that gives us a single integer. Right. So if
When I run it, I don't have that problem.
I guess you still have to still have to put EP00.
This is the issue, right? This was the issue all the way. Yep, it's giving me 0, which is not very interesting. I'll look at another step which has some non-zero information in it. For example, this one. Or is there one which is more interesting? Let's try. I'm just looking for something where there are ones like, I think this is 7. So the 7th step in the episode. Let me confirm. Yes, so it has at least one over here, and then the state is also 1. So we'll try with this one. Yep. This is giving me 24. Now it will depend, the exact number will depend on a few things, which is how you, like which order, which actions or which directions you picked in which order. So in this case, it's north, east, west, or south, and also how much weightage you are giving to different numbers. So here south is multiplied by 8 and north is multiplied by 1. But then
Yeah, I think you have to align your endianness in the decoder to my encoder.
Right.
We did a reverse.
Right. So then you have to implement the decoder part, which is just it will undo what you did over here. So it will take this number 24 and it will split it into this 1 and the north, south, east, and west. So I'll try doing that here. So, west to south. Let's see if this works now. Oops, I'm getting 1.5. Oh, right? So we're getting back what we started with. So only the order is different, but if you look at the keys, so south is mapped to 1 and then everything else is 0, right? So we sort of have this implementation now. Now we can go ahead and use all the algorithms that we were doing earlier, right? Because there will be a subtle change over here. So because this state S is going to be this complex blob of information which has all of this. So you want to convert that into a single integer, right? And the way we are encoding it, that means we already know that the number of possible states is going to be 320. So we already know this size over here because this variable is no more available to us, right? So we can't query the environment anymore. But we do know that the way we have observations, and the way we are encoding observations, this number is going to be 320, right? So I'm not really going to run this right away. There are only two changes: make this 320, and then wherever you are using a state directly, you will have to convert it to an encoded observation, which should be an integer.
Why don't you just do the encode out? Like I just did it right inside the observation function. Like why not just return in your foolsball the encoded? Then all this code actually works without any changes. Like
Yes,
if the
you are
observation
saying
returns that.
you are saying inside the observation functions, right? Inside
Yeah.
the observation function within the class. Yes. So there is a reason why I didn't do that. The taxi environment is already doing that for you. Why I didn't do that was that because I wanted to talk about what will happen in a more complex world. So for example, if we were dealing with a real video game, so the observation you would get then is will be just a snapshot. It will be one of the frames from the video game, right? And then it's pretty much on the algorithm to be able to convert that observation into a single integer or somehow map it to an action, right? And that is sort of what we will do in the next course, where we will use neural networks to map any sort of high dimensional observation into a single number or a bunch of small numbers. So that is why I didn't include this as part of the environment, although OpenAI is doing that with Taxi and other environments. They're directly giving you an encoded state, right? And also because with this sort of a setup, it's much easier to debug things because you still get non-encoded observations, so you can sort of make sense of what is going on versus having to look at an integer, and then you will have to explicitly decode it and then look at the information. So I think that in a general case, the environment will not give you encoded information. It will just provide you raw observations. The observations depend on how much the environment is willing to share, and also how capable the agent or the algorithm is. This is something we talked about in the very beginning when we talked about what the state should be, right? So generally, people make a distinction between a state and observation because the state is like the whole thing, and observation is what you are able to observe, or what the environment is offering you in terms of information. So that is why we have implemented here. But right now, the next step that we need to do is sort of make those small changes over here in this algorithm, and then here and here, and then see how much effort it takes to fine tune the parameters again, so that your agent is able to learn the behavior of the new environment and it's able to play the game correctly. There are a few things that we discuss. What sort of movement should be considered a collision, and then how should the reward structure be? Should we detect instances where you had detected an opponent in front of you and the opponent just a collision was averted because the opponent moved out of your way on its own, but you didn't take any action? Should that be also penalized? Should there be a penalty or reward for that? And I'm sure a lot of other questions will crop up when you look more closely at the problem and try to you know try to learn the right policy for this environment. But at this point, we are So if we are able to solve it with the existing techniques, and we should be, uh, then we can make the world even more complex. We can make it bigger. uh, just the layout should be bigger, introduce more players, introduce more AI in terms of how the players are approaching the game, right? So that you can in fact build a system where both the players, like the opponent and the player, they are both trying to learn the policy, and that is something that we will do in course 2. But now we are sort of set up uh, for using this environment for more complex tasks, right? So it's no more a toy problem. This is looking more and more like at least video games, if not the real world. And that is something that we are going to do a lot in course 2. uh, Consider it like a homework. So if you get time, try to implement these algorithms. We already have everything written in terms of the functions. So make the small changes, then tweak your parameters, and see what kind of performance we can get, and try to debug instances where we are running into problems. It could, like, we cannot be certain that the environment and the reward is error free right now, but that is something we want to learn through interaction. So try to do that, and then we will discuss the results in Monday's office hours, and we'll also talk about project submissions in Monday's office hours. And in terms of the syllabus, there is only one bit remaining, which is dealing with continuous spaces, be it your action space or be it your state space. They have remained discrete so far. We had cells where the players could move. We had only select actions south, east, west, north. But we would like to at least look back at the car environment that we had in the beginning, and think about, if we want to solve that environment using the techniques available to us, how are we going to do that? So we'll basically think about discretization, and if we have time, probably quickly implement some sort of a discretization for the car environment on Monday, and see if these algorithms work with the environment as well.
I don't see schedule for next office hour. So
uh, I'm not sure. So that could be because it was supposed to be a 4 week long course.
yeah,
But we use the first office hour as an introductory session, and of course office hours only make sense after a week is done. So I will inform Mariza about it, but if you can reach out to her and inform her as well. We definitely need the next office hour, because there's a fair bit of things that we need to cover in that session.
okay.
Cool.
So with respect to the second course, when it will be started, any
Yeah,
thoughts?
I'm checking with Marissa. So the initial idea was that we will do it in the very next month, like when this course gets over. So, for example, everyone has time till 7th April. So the Thursday and Friday after that, we can start with the next course. But I will have to double check with Marissa, because there are a few other things, a few other variables that we want to look at, and then decide when we want to start that course. Okay. Any other questions? Any confusion with related to this or the project work?
I was wondering on the project if we can play around with changing the rewards as long as we put it back when we calculate whether it's meets the between 9 or 7.2 or whatever the new number is.
So you mean changing the rewards and then training on the change reward, or just for the sake of?
Exactly. Yeah. In other words, can we try getting better performance by training on a different reward scheme, even though I
Yes.
think
Yes. We can do that. So as long as you are able to meet the requirements of this project, obviously the first, if that is the first requirement, was passing the project. But once you meet this requirement, then please go ahead. If you are interested, then modify the reward structure. And we had a few discussions about what could be done. Like for the pickup, you could have a separate reward, and also think about where things are going wrong. We will cover some of that in the next course. uh, but for example, there's the idea of experience replay, right? So if you just look at bad instances, bad episodes, and see why, what is fundamentally going wrong and how could that be fixed, right? And I'm sure we'll come up with new ideas.
And similarly, can we change the state encoding? Like we just talked about doing a better state encoding for this, right? Can we change the state encoding rather than having the 600 states?
Yeah. So that will be additional, you can consider it challenge work, but it is not strictly a project work. So the project work is just to get 7.2 and 8.2 performance, but I would really like everyone to go beyond that and really experiment with the environment, change these things around and see how far you can go, because these restrictions are uh, sort of just the baselines. We want to learn a lot more.
And is there a place where we could find all of the class recordings for the
Yes, so you can find them in two places. One is, of course, the YouTube channel. So I keep sharing YouTube links, and if you go there and see, you'll find the entire playlist, which has all the videos, uh, and they are named with the week and the session, so it's easy to find it. You can also find it in Slack if I just want to show you for a second. Yep. So if you can see my screen, and I have our private channel open right now, right? So there are some pinned messages over here, right? And if you look at these messages, one of these messages has all the links, right? So I typically update them at the end of the week. So right now you have everything up to week 3 office hours. I haven't updated week 4 right now, but all the links to the recordings, the slides if there are any, and the starter code and the solution code, everything is here. Of course, because we have organized things in a particular way, so you can also directly go to GitHub and go to either the master branch or the solution branch, depending on whether you're looking for the starter code or the solution code, uh, and select that. Sometimes things have there are instances where the starter code is in a particular week, but then the solution code is in the next week's office hours. So it's better to just look up this list over here and find the resources.
So for all the 6 criteria for the project, are we writing all of that in the Jupyter notebook?
You're talking about number 6.
Like all the describe the message and the variable and all the other things, like how do we submit it in terms of the format?
Yeah, you can do it in the Jupyter notebook, and if you want to do it separately as a markdown file or a PDF or a Word document, that is also fine.
Okay, and how do we create the Jupyter notebook?
You can use Google Colab, or if you want to work offline, then you would need to install Jupyter and the libraries, which will require some sort of a Python installation like Anaconda, or using Pip. I think it is far easier. Like if you don't have an installation, it is far easier to just work in Google Colab, and then just go to file and download your IPython notebook and share it on Slack.
Or like, are we downloading as the IPY and B? Like, is that the
IPY.
Jupyter notebook?
Yeah,
I see. Okay.
that is the Jupyter notebook. That will just allow me to again upload it to Google Colab, and I'll just confirm the results. That is the easy.
Okay.
How do we submit the project to you, Farhan?
You have to DM me. Just send me a direct message on Slack, and that should be it. And
Okay.
of course, you have to attach the file.
Okay, thank you.
Sure.
So you were saying it's okay if we have, for example, a Word document with the documentation and just a Python file with the code rather than Colab if we want to work offline?
Yeah, so from my perspective, it is far easier if everything, at least the code is as a Jupyter notebook, not a Python script. But it's okay if you are able to submit a Python script, I'll accept that as well. And then that should be accompanied by a Word document with the whole description. It's
Okay,
just
so all the
easier for me.
go ahead.
No, it's just easier for me. If it's IPython, I can just upload it to Jupyter and run it. Sorry, Google Colab and run it there. But if it's a local file app, I also have a local setup to run things. If it's a script.
So we can just make it into one file, and all the description for the first few components, you can just write it there in the Google Colab as well, right? Just as a text or notes, and then
The easiest thing for everyone would be just to have all the documentation description in the Jupyter file itself.
Yeah, okay, got it.
Sure.
So we just save it in a Google Drive or so, or Jupyter Notebook.
You should save it to Google Drive, probably also to GitHub, because in the longer run you want to maintain the history, the different versions. I sort of showed you how to do that. I think the first or second session was basically in the file menu you have an option to either save it to Google Drive or save it to GitHub. And if you try to save it to GitHub, then you will have to log into your own GitHub account and provide it the credentials and authenticate to itself. If you have a GitHub account, a public facing GitHub account, and if you choose to upload it to GitHub, then it's fine. You can also just share the GitHub link instead of downloading the file and sharing the file on Slack. The GitHub link should also work.
When is the due date?
It's 7th of April. Sorry, 7th of May. Okay, then I'll wrap up this session. If there are any questions at all, feel free to ping me on Slack. I'll reply there. I'll also reach out to Marissa, but if you can reach out from your side, it would be great, because we definitely don't want to miss out on Monday session. I know it's not a schedule on your side. The link is still the same. So, but yeah, we just want to do that. We definitely want to do Monday session.
Okay, and lastly, for the percentile for 7.2 and 8.2, should we be consistently getting that every time we train with those hyperparameters? Or like if it reaches that, like when I run it once through and it reaches it, is that good enough?
I think if you get it once, that should be fine. If the number of episode is small enough and you can just run it a few more times and just be doubly sure that you're consistently hitting it, that would be great. But basically, because I asked in the project instructions, I said that you shouldn't remove your output. So I'll be able to look at your output, and if you were getting that and I'm like getting a little on the lower side, that is still fine.
I see. Okay.
Cool. Then I'll see everyone on Monday, and probably by that time we will have clarity about when we will start the next course as well. Thank you.
Thank you, Farhan.
Have a good weekend. Bye.
Thank you.
Thank you.
Thank you.
Thank you. Bye.